The concept exploration of a respiratory rate monitoring garment using digital zero crossing. The respiratory rate is a key indicator of physiological and mental distress and overall human health. Respiratory compromise is one of the most common reasons for ICU admissions, but difficulties in monitoring by manual observation can arise due to patient movement, conscious and unconscious manipulation of their own breathing rate, manual error in the observed monitoring or counting, or even neglect of the measurement altogether.
The resolution. Conductive thread stitch sensors provide custom integration into everyday clothing while delivering ongoing monitoring with increased accuracy and frequency. Stitch sensors are a minimally invasive method to monitor pulmonary movement. This is done so by analyzing the resistance versus displacement measurement of the stitch sensor, thus counting inspiration and expirations as events. When the chest expands, the stitch sensor is strained, causing displacement, thus a decrease in resistance. Pre-trial testing of the silver conductive thread was completed using a tensile testing device called the MinStrain. This was used to measure the resistance versus displacement observed on 6 12 by 4 centimeter samples composed of 87% polyester and 13% spandex. The samples were placed in the MinStrain and displaced for a total of 197 seconds while measuring the resistance versus displacement, thus simulating breathing characteristics, and surprisingly, as displacement increases, resistance decreases, creating a linear relationship.
The silver-coated nylon thread was stitched into the garment, and the sensor was placed 8.5 centimeters from the axilla at the xiphoid process to measure maximum thoracic expansion. Sensors were secured with ring snaps for easy and secure connection to the microcontroller. These ring snaps were insulated with neoprene fabric to avoid shock and discomfort of the user. Silicone wires were then soldered to the socket of the snaps for easy wearable connection of the garment to the signaling processing system. A quarter Wheatstone bridge was used to measure the change in resistance of the silver stitch sensor using a digital zero crossing approach. A reference point of a known value was noted at the potentiometer site, and a changing value was seen at the sensor. This was connected to an instrumentation amplifier circuit, and the differing voltage between the reference and the sensor arm was amplified to see a change in respiration. When the signal is seen, a lower threshold and a higher threshold are noted, indicating a low voltage and a high voltage reading. The difference between the threshold is where a breath is counted, but only when both thresholds are crossed. Digital zero crossing can save energy and be a simpler computation than a fast Fourier transform, allowing for a more accurate monitoring of respiratory rate. Garment testing was completed on 4 participants at this time, 1 male and 3 female, ranging from 20 to 39 years of age. Body mass index was recorded and the chest circumference was measured. Each participant sat in a chair and 2 independent monitors recorded manual observations of the respiratory rate for a full 60 seconds, while the sensor recorded the respiratory rate as well. Sensor count and observed count comparison was conducted with a y equals x line. Average manual observations are seen on the x-axis and sensor observations on the y. The closer that the values are to the x equals y line indicates more agreement between the 2 methods of counting breaths. Below the line, the sensor was undercounting. Above the line, the sensor was overcounting. Observers on average counted 2.44 more counts than the digital zero crossing sensor. Sources of error can be seen in the sensor count and also in the observer count, and in future work we will be attempting to reduce these errors. Further research aspirations incorporate the improvement of the garment design and functionality. This entails producing custom-fit garments and placing sensors more accurately, implementing a full Wheatstone and replacing the current quarter Wheatstone bridge to eliminate manual calibration, increase the participant pool and seek IRB approval. We will also look into fatigue analyzation of garments and testing it after being laundered. We will test during dynamic movement and for longer periods of time. And we will incorporate a self-sustainable energy source. From all of us here at the Aspire Lab, we would like to thank you.